Okay, so let's see what we did in understanding regularization in why we imported these libraries. We want to understand what is regularization. Okay, then what is dropout value. Okay, we loaded the data. This is how the data looked like. Okay, you can see a few column that we intended to convert into a vector, right? So that is what this function did here. It converted those column into vectors. That is your season 1, season 2, season 3, hour 21, hour 21 to, right? This is all numerical column. So now, my voice is audible, right? The messaging that it is not.
Yeah, it's audible.
Okay, okay. Yeah. So this is what we started. So we had this bike data, which has some distance travel, and we just simply loaded it and converted into one odd vector. And the video recordings uploaded in case you missed, but essentially it doesn't matter. This is a vector format of the entire data is converted into zeros and ones. Okay. Now let's see. Okay. After that, what we did is we divided the data into train and test. Okay. I mean, this is pretty easy Python code. Okay. We divided that. Now the important part here is in keras. So in keras, we created a sequential model. Sequential model is typically layered model, right? Okay. And here we are creating a dense. When you give dense 250, what is the input features here in this case?
Input is 57. We reduced to 12 or something, right? It should be the data that.
Yeah, data dot. If you see, you'll see input number of features. Okay, but I mean, it is fit to that. From there, we had 250 units, right? And X train shape will give you how many shapes, how many input features it had. And this is the activation function. So you can see 250, 150, 50, 25, 1. So at the end, it is linear. Which version? 250 is number of neurons in each one layer. Okay. So 250, 50, 150, 50, 25, 1. Okay. At the end of putting everything, so see what you do in case you're doing linear, right? You'll make it linear here. You'll put MSE, mean squared error. Okay. The loss function is MSE.
Having 5 layers totally.
Total 5 layers. This is your MSE, and this is your optimizer SGD.
So here activation, we use softmax or this one, right? Can we use linear means? So what does it do? Does the we plot in a linear way or like
MX plus C.
plotting MX plus C?
Right, right, right.
Okay. So this is from the hidden layer to the output, one output, then the last one.
The last one, right?
Line.
Yeah. So if it is classification, you'll use softmax.
Ah.
If it is regression, you'll use linear.
Oh. Okay.
It is the activation function for the last layer.
Oh, okay. So in the last layer, either we can use only softmax or linear, depends upon the problem.
Yeah, exactly. Depends
so
on
ReLU and sigmoid we cannot use from the output layer.
Yeah, I mean sigmoid, if you do it, will do by classification. So if you want to do multi-class classification, you'll use softmax. Yeah. So there are 4 or 5 options. So if you just do the help of this, linear is definitely for linear regression. Softmax is there. Okay, sigmoid is there. So options are there. Okay. So here you are mentioning the optimizer name SGD, statistic gradient descent, and Adam also you can come. And you have this MSC matrix. This is a scoring. Right? I mean, based on what? This is the accuracy. Okay, based on that, this it will show. Actually, right. Number of epochs is how many times this. Remember the for loop that we created in range 5000, all that. This is that. That means how 4000 times it will run, and each time it will run with 1024 data. Fine, right? Okay. So after that, you are calling this fit function. You have X train values, Y train. This is the target column. Okay. Validation data is equal to exchange values by the CNT column. CNT column is basically count. It's a continuous data. Okay, count. If you bring it up, you will see some number associated with that. Okay, some number. So this is count how many times the cycle ride will happen. Okay, sorry. Batch size is equal to batch size. This is whatever epochs is or epochs that you configure and verbose. Now let's see what happens. Okay.
So this is already has run the output.
Yes, the output the model training has happened. Now very useful stuff actually. Okay, so you do model.summary. Okay, if you do so, it will show how many. It will show how many layers each layer and the output data. Understood, right? And it can tell you how many parameters are there also.
Feature columns.
Parameters is your coefficients, right? Because neural networks is about, derived parameters and the coefficients. So this is the number of parameters. Initially, I think something around. No, it was than that.
Initially, 57 or something. Later we did a feature engineering and drop out.
But we added because of this kind of data.
We can print
Here I cannot see the data in the variable as a pop-up, right? In Spider or the variables, there is a box called variables. So there I can double click and see what is there in that. But here we can't see that in Spider.
You can take your mouse to that and it will show. That is what you
No, not like that.
You can double click and open in a separate
Oh, no.
graph.
Even in Spider we can. So there itself we can delete the object if we found unnecessary.
Oh, is it? Okay.
Yes.
57. So from 57, main variables, we have some 60,000 derived variables.
It's deriving by itself.
Yeah, that is a neural network, right? Is it connected, fully connected? Okay, so yeah, from there it is actually driving.
57 to 60,000.
Yeah.
So each layer has first we are doing 250. It will do addition. Oh, total columns, adding everything.
Adding everything, yeah.
So
Absolutely.
each layer will be. So internally, how it does the
Suppose you have 57 variables. Just let me do with two variables. Okay, or two variables. You have x comma y, x square, y square, x y. These are derived variables. It is finding parameter for all of them. X cube, x square, x y. You can have infinite actually. Right, with that. Okay, with that. So here also it is just finding 60,000.
So all these 60,000 are really important, or do they make any sense?
Yeah, here when it actually, that's what it will try to zero it out wherever it thinks it is not important. Okay, and yeah, it will try to zero. So I think I have saved all the information. So let me plot the graph. But it will actually, that is the purpose of neural network. There is something known as gradient vanishing. Okay, I mean, and there is something known as overfitting. Overfitting you have seen. Gradient vanishing means it is not, the gradient is not changing itself at all. Okay, not, yeah, it's not converging. So that was the problem initially. A lot of with this is a basic neural network with no convolution, nothing there in it. So that was a problem. Earlier people faced. Then they have used activation function, improved a bit. Then they used CNN and well, improved a bit for computer vision. Okay, let's see. Yesterday I told you, right? Training and validation, the difference between them. Okay, so what does it mean? It means it is a case of overfitting, isn't it? Okay, where there is a increasing gap on training and validation, it means there is some sense of overfitting.
So now we have to regularize them on.
Right.
But the error is reduced.
No. So this is the loss function. You can see here the training. This is a validation, right? And this is training. So training is reducing, but validation is not so. Okay. So if you want to see.
So we will try to reduce the number of features.
We will use our regularization technique to reduce it. Okay. So this is the after 6. I think this is pretty much point. Okay. So
we
that
use lasso or registration.
No, we'll use regularization. Okay, lasso and reach, we are using neural networks basically. Here, lasso and reach don't work. That is like a normal regression. This is the regression that we are doing using neural networks. Okay, so here we will rely on regularization techniques. I mean, which is not lasso and reach.
So what are they called?
There is one called L2 regularization. Okay, there is one. L2 is I mean, the some way root it is same, but for neural network, it like your softmax and heuristic, right? For neural network, it will have some different manifestation. Okay, so I mean, the thing is internally they have entire literature around it. Okay, that's why I'm not saying not to compare because they have a separate literature. Okay, I'll do this almost the same stuff. Okay, but I'll add this time some regularization over it, huh? Because see here, I mean, the entire regularization is the part of my this. You see here, regularizers. This guy. Okay. So
this regulation is specific for keras type or like TensorFlow there is a
I mean internally all these things are implemented. You might have to write some more code there.
Oh, okay.
Okay, these are like in an abstracted format.
Okay, abstract
so once you understand the logic, once you understand why it is used, then coding is, I mean, the definition to that is pretty much you can infer it. If you see that code, you will be able to comprehend it. Okay, so what I'm doing now, I'm creating. See here, I'm creating another model, and in this another model, I'm passing this kernel regularization is equal to regularization.l2.
It's L2 dot.
Yeah. So if you do regularizers dot, you'll find few varieties. One of them is L2.
Okay.
Okay, and these are the two parameters we are doing regularization in these two layers. One is this last layer, one is this layer. You can do, I mean, this is one of the parameter. Of course, you can do it in other layer as well. Okay.
How do we get to know?
Yeah. So that is what is called hyperparameter tuning in neural networks. Okay, how do you find out which one is better? Okay, I mean, there is a chapter on which we define. Like, I mean, this is a perennial thing, right? Actually, I mean, this is a subject separately. How do you find out? And that is the entire research about. If you see somebody is doing research in neural networks on a particular thing, he's typically finding out what is the best. Because permutation combination is huge, right? Okay, how do you find out which is the best? Okay, but most theoretically, most of the problem, relatively common problem, can be solved by one layer and with a fixed number of neurons. Okay, most of the common problem can be solved by one layer. This is a standard jargon that people will say that uh, if you try to tell okay more than two layer, the first question they will ask is haven't how did first one layer work with you? What is the best thing that you got out of one layer? Okay.
What is that point of the
Hmm?
Jump size.
No. This point. Oh, sorry, I forgot to mention. This is your regularization parameter. Okay, in regularization parameter, it is typically like lasso and ridge. We used to give one parameter to beat the edges, right? Lambda. So that is what it is actually.
The basic idea is you're trying to make some coefficient parameters to zero.
Make some reduce the coefficient parameters. Okay, or diminish some of them. And that's the idea of regularization, right? This is how you do it here. If you think 0.05 is 0.005 is too less, you can try this. What is the result coming with this? Then change that to. I mean, you'll have to iterate through various stages actually to find the optimum values. Okay, just to get a sense of it. Okay, this is how you do it. Okay, I mean, fine tuning is something that will come once or twice. We do some rest of. Okay, so here, yeah.
Takes time to compile.
No, it's done. It happened pretty fast.
Can we use L1 also?
Hmm?
L1 regulation.
See, I'll show you the regular. You see, you have all these options here to regularize it. Yeah.
Can use any of them.
Use any of them. And which one to use is something that we'll, learn during our tuning. Oh, this is model creation.
Yeah.
Right? Let's train it.
So training.
I thought I already.
That's what actually. Because you said it take more than 25 minutes.
Yeah. So,
The same thing.
okay. So again, it's the same stuff. Model. This is the new model name. Okay. It might take some time.
About the same thing, 4,000 it will do.
Yeah. And after this, after this process, we'll see that the difference between those two things has diminished. Yeah.
So even the edges will go away. It will regularize all the heights and everything, right?
No, I mean, it will definitely smoothen that up, but more importantly, you'll see, the difference between the two lines, right, getting reduced.
So divided the data set into three parts: training, validation,
So validation is something that is taken from the training data itself. Okay, let it happen. Hmm? 90 and 10%. Training and validation.
Training and validation. Training and test is?
Training test is up to you, 80-20 general rate. Okay, let it happen. Okay, one more thing before I move to CNN is tuning the loss function. Okay, so as of now we have seen a few loss function, right? Like sigmoid for logistic, we've seen sigmoid, right? MSC for linear regression. We have like how do you find out which one is best? Then you can try configuring more things in one you call model.compile. But if you do here, it's not showing up here. But anyway, I mean, if you see the documentation, you'll find that apart from the one that we are configuring, right, sigma, I mean, there are for last station, we have binary cross entropy. Okay, so maybe I'll have to refer to documentation. Okay, so whenever you are trying the stuff, if you want to really test it out with a different loss function, you might want would have been done the same way that we did for ReLU and Sigmoid, right? Different loss function, you give it a shot, see which one is working out for you. So that is typically how do you fine tune loss function. Okay, so let's have a look at loss function. You have inside one, you have, for this is mean squared error. Yeah, mean absolute error. You have all these options. Absolute percentage of square hinge, right? Square hinge, categorical hinge, log cost, categorical cross entropy. This is what you have seen. Binary cross entropy, sparse categorical, Poisson, cosine, right? So you might have to find which one among them is working out for you. Okay, and now, got it, right? So you might actually, this is how you're, this is one way you're doing it. Another way to do this is like this. Keras, from keras import losses dot issue. So it will show you all the list. Binary cross entropy, you can see all this stuff. Understood, right? So that is how you give it a shot, actually. Okay.
Is dropout different from manual and to regularization or register?
Dropout is a little different, right? Yes, we discussed dropout. How dropout would work is between, it will, make the candidate, if we give dropout is equal to 0.50, it will make the edge subject to recalculation again, right?
Are we using dropout and this?
Yeah, we configured dropout, right? 0.75, like
Dropout we didn't use it.
Using L2.
Regularization only.
dropout region is very, yeah. I think no, I didn't use dropout. I think earlier I was using dropout or not. No.
No, we could use. I think that
Somewhere I think I used
probably
dropout.
that is where the dropout.
Here won't be there.
Yeah.
I should use it here on the wallet.
Yeah.
Yeah, we didn't use it actually.
Oh, I had this impression that we used it.
Some other data, this one we can use it.
Okay. Yeah. Just 1 second before I. Okay. So now.
We have different optimizers. These are the two things.
Yeah. Optimizer you have to do.
Optimizer and autoencoder.
Dot.
Autoencoder.
Autoencoder. I'll just give a brief now. I mean, this is introduction to autoencoder. Later on, we'll there will not see, and after that, before GAN, right? Autoencoder is we will see details over there. So autoencoder is in normal machine learning, you would have seen feature importances, how to extract important features. That is what the autoencoders in neural networks.
Similar like how like PC.
PC. Okay.
PC.
Like if you have a complex data, you have to find which are the important features from here. We'll use autoencoders for that. Okay.
Same like byte data set, we talked about a couple of features, right? So there we can apply the
autoencoder and find the important features and all. This is part of feature. Like what does it? I mean, just briefly. Okay, so you have data. What will you do? You'll actually converse. I mean, you'll have some number of units at multiple layers, and your end data also will be same size. What you try to do is you try to see if by encoding and decoding you're getting the same data. Okay, and in the encoding process you will minimize the number of features. In autoencoders you'll see you're actually minimizing the number of features, tapered. Okay, and then it will again grow up, and you'll see if from these minimum features are you able to replicate the actual stuff. Then that are the important features. Okay, you have suppose 5 features as input. Okay, sorry, you have something which is represented by 5 features. You minimize the number of intermediate nodes in all the hidden layers till one point. Okay, what are you doing till now? You're encoding. Encoding means whatever major information you have, you're reducing the number of information that is required to represent that. Okay, after that, from the encoded information, you're again generating the actual data, which is of the same size that of actual data. Now you see which is the best feature from which you are able to get the best data.
So we'll do a couple of iterations of sending different input features.
Right. Suppose you have a face data. Okay, you'll see, and let's take a basic case. You have to identify if the person has eyes and nose. Okay, so you will from all the data, when it is taping up, when it is getting smaller, it is finding important features, most important features. Okay, when it reaches till this point, okay,
The lowest point.
yeah, the lowest point, when it reaches to this point, then it again try to decode. Right, it encoded here, that it tries to decode. Now when it tries to decode beyond a point, okay, when it tries to decode beyond a point, I mean, it should be again creating that the same data as it started with. Okay, if it is able to do this, those tapered feature, the minimal features that is capable of doing it is the most important features. I'll talk at length about this, but this is what autoencode. This is actually very simple concept. Okay, it is just finding important features. How do you verify? You verify, from the smallest feature, if you're able to recreate
All features.
all not all features, recreate if you're telling from the important feature, so you're able to tell this is a cat, this is similar to that, then it is an important feature, right? I'll go in depth, and that is where GAN is like a little modification on it. From GAN, what it means, from compressed data, from very lesser amount of data also, you will be able to regenerate the actual data. Okay, it's like GAN is okay. That's the modification. That's it. Okay. Now we'll see how to do these optimizers. Okay. Okay, so what will I do? I'll try to use various of
Optimizer and dropout also we are trying here. Optimizer and dropout also.
dropout. Yeah, we'll write it here. Yeah.
So many importance. So many things are very important.
Optimizer different types.
Other things are pretty much we have seen before, right? Callbacks, early stopping, model checkpoint. This we have seen before. This is really required, and these are real optimizers. There's GD, ADA, delta, Adam. Adam is something that you will use a lot in CN and other things. Okay, Adam, Adam, add max.
So keras uses TensorFlow backend.
Backend, yeah.
And TensorFlow uses C++ in backend.
TensorFlow is written in C++.
Which one?
TensorFlow is written.
That's why some programs, I think you were saying, right? Some programs will write in C++ directly.
Oh, even the code actually they have written in the kind of C++.
TensorFlow is written in
C++. We can write in C++.
Yeah, you can talk to TensorFlow in C++.
Oh, directly.
Actually, a lot of companies do that. I mean, but as you understand, doing that would be a little difficult.
Yeah, it's not that keras has support, but I think only keras and TensorFlow only has support mainly Python. Remaining if you take CNDK or Cafe2, they mainly use C++.
C++ is extensively used. Python also they use it actually.
They use it actually.
Python is popular because it is very easy to integrate. Okay, data cleaning task you can do it very easily if you do just using seeds. So if unless there is a case of optimization like performance, which anyway this data structure is good enough because in the backend it is all C++ only. But still, if there is some case which Python is not able to handle, then they rewrite into C++. Okay, just load it. Now let me load the data.
Here it is showing using TensorFlow in the backend, right? So if you use any Piano or something, so how does it identify since we didn't have any other framework it is showing as TensorFlow backend or like how is it there?
Actually, then you have to configure. You want to use Theanos as a backend.
No. So how, because it is clear.
But that is by default TensorFlow. If you don't give anything, it is TensorFlow. If you will have an API using that, you can configure if you want something else.
Oh, then even from keras you have to add Piano kind of it.
Yeah, Piano. I mean, Piano library you have to install it separately and connect the packages. Actually, that's it.
There's keras.
The same code would work. You don't have to change anything in the code. Same code.
Oh, okay.
Backend itself.
I can. Now the idea is the same code would work. There will be of course some delta, something not supported and all this will come, but more or less it works. Okay, so now wait, for this I'll use some other data. No, I'll use some other data.
You can directly give a link also. Only to download the data set actually.
Yeah, you can do directly give the link.
I used to because
you can do that, but
because I trade SK minus 32-bit and I am from Collab. It takes from cloud. So we cannot put the I just give the link.
If it is not protected using something, you can actually give that. It will work actually. Okay, so this is how the data looks like. Okay, so you have what you wanted to predict. You want to predict quality. Okay, based on these other features. Understood, right?
So the quality will be a continuous value, right?
Continuous. Oh, it is semicolon separated, right? No, not 2 equal to 1 equal to. Fine, right? Okay, this is what you have to predict quality. Okay.
How many rows are there? How many rows?
Rows, if you want to see.
Uh,
1600. Yeah, 1600. Okay, now what do you want to do? Yeah. You want to create feature X, feature Y. Okay, this is what you can. Data quality is your Y target. X is data drop quality, and this is a decent way to do it. Okay, dot drop quality and X is 1. It will drop that. So X and Y is this.
So remaining all column here constraint.
Yeah.
1 plus 1.
Right. So now, of course, what you want to do is you want to train test.
Train test.
Yeah. Train test and validation test. Okay, so X train X test. The entire data set it is dividing into this. X train X val. This is your validation data set.
The second line is validation.
Right. Okay. I mean, X train data, it is breaking down more on train data and validation. So you have three varieties: X train, X test, and validation. That's it. Okay. So now we want to create a model, and in the model we'll pass out, like, this is one way of tuning it. Okay. This, so far it is clear, right? Nothing fancy with it. Okay, now here you see this is model creation function, and remember, whenever we are creating a model, we can pass optimizer, because the objective is to test with different optimizer, which optimizer is working out for us. Okay, so this is the case. So here, based on this optimizer, okay, in this case you're not using anything, right? I think we removed it.
Number of neurons in each layer, should they be gradually decreased after the consecutive event? Or if you're decreasing 150, 25 times?
This is, I mean, generally when you're creating this layer, right, it should generally be half of the previous one. That's okay. I mean, that's a usual. So when you do so, right. So, but if you go for CNN autoencoder, there it is mandated. It should be like this. This half of the previous one, of course, gives you good results. And
That 100 assets like random.
yeah, it is random, and after that it is reducing by half. By half.
And even the number of layers also, that is also it's up to us.
That is up to you, absolutely. Okay, so here you remember you guys are asking that how when to stop. Okay, so this is like early stopping function that you can configure. Like this is these are the callbacks. Okay, that will happen every time this guy is running actually. Okay, every batch this will be getting callback, this stuff. Okay, so you are configuring model checks. Okay, these are about some model parameter that it will check. Okay, then this is the early stopping, when when should the train the current model should stop. So this is what you can configure. I'll come to that. Okay, but you can have this sort of controls. Okay, I haven't discussed a lot about callbacks, but you can have this sort of controls. I mean, yes, last time I think we gave some prints in the callback, right?
Yes.
Yeah, we used one callback. This one, right? We implemented this, extended this callback class, and on batch data and what should happen, right? This is what we configured. So callbacks is a way by which you control the learning, iterations, learning, whatever things you can control it. Okay, so the same stuff we are doing it here.
It's like the for loop iteration.
Yeah, for loop. I mean, you want something from your side to happen. When you're writing for loop, you have total control of the entire stuff, right? Yeah, here you just call the fit function. You don't have a control of the entire stuff. So how do you get control? It gives you a hook. Okay, you can hook. You can actually register this hook. After that, whatever there is the hook, it will execute after every iteration. Got a hang of it, right? So this is like you are latching onto the system, right? So this is your callback function. I haven't used it so far.
So you're doing it to the patient's parameter.
Hmm?
The patient's character.
Patients, these are, for, I mean, this is not the only two callbacks. There are a lot of other callbacks actually. Okay. So what you do, you will try to find the accuracy, clean data and validation data, and you'll wait for 200 times. If it is not varying a lot, you'll stop it there. Understood, right? You are finding some accuracy. If it is not varying, it's not changing after till 200 iterations, you'll stop it there. That is what it means. Huh? Verbose is just to show the logs. Verbose level 2 means till what level you want to show the log. Verbose throughout, right? I may not have spoken about it a lot. Verbose means, whenever you're training, what is the information that it will show and all that. That is controlled by verbose.
So
Okay, then you have model checkpoints. As model checkpoints. Okay, so what is model checkpoint? So at every stage of learning, right? This is a very in TensorFlow. This used to be save and restore concept, which is internally getting. So in TensorFlow, what used to happen after, like, remember, this model training takes a lot of time. After 5 days of model training, if it fails because of some reason, you might have to repeat the 5 days work, isn't it? And you would like that? No. What will you do that? You will like to checkpoint the model at various stages.
Oh.
Okay, that after 100 iteration it point is 200 and checkpointed. If something is wrong, you don't have to start from zero. You'll start from wherever you last checkpointed.
Okay, but it will try to run continuously. So based upon our checkpoint, we can.
Yeah, checkpoint means it is what does checkpoint means? Whatever is the current state of the data, it will store it and it will resume from there again. Okay, because these are extensive learning. You're seeing me how much data, every like 1,000 data, 2,000, 5,000 data I'm using now. Even then, it is taking a lot of time. Just think of if you're an engineer working on a system which has a lot of data and this thing, your 2 days work would be like this thing training. You cannot just let it go like that. So that's why this checkpointing is very important. This is mostly available on TensorFlow compared to others.
So then patience equal to 200 if you give. So now if we found any error, the loss is not, as you said, accuracy is not gradually increasing or something. So our execution will stop or it will still continue?
No, it will stop.
It will stop.
It will stop. Okay, that is why early stopping.
Okay, so then we have to fine tune the model and then we can.
Then we know that we don't need to have this much of iteration. This is fine enough. Okay, then you see here. So you have it's quite configurable. So you can say save best only. Okay, so what it will do, it will, rather than saving all the models at every iteration, it will store the best iteration, best model so far. Okay, and verbose 0, that means no logs. That is what it means. Return callbacks. Okay. Now, great. Okay, everything so far. But what is the important thing that we want to do? We want to try with various optimizers. Okay, so there are a lot of optimizers. Okay, SGD 001, Adam, ADA Delta, RMS prop 01, Adam, and Adam X. Right, we have all these optimizers.
Using everything.
Yeah, we want to try with everything. The other guys hadn't stopped so far.
So this is something like gradient deletion, right?
Yeah. So this is like in you might have heard about grid search in Python. Yeah, you have grid search for hyperparameter tuning. Okay, this is something similar. Hyperparameter tuning means every model has some parameters that can. We stored all the parameters and try out which one is best. Right. Okay. Okay, if you haven't come across, you can note on grid search actually. Grid search. So it is used for finding there are a lot of parameters. That's what, right. In models also there are a lot of parameters, number of neuron this thing. How do you configure? How do you find out which one is best? That is done using hyperparameter tuning. Okay, so what we want to do? We want to loop through all the optimizers. Okay, this is your batch size is the number of epochs 1000. Okay, so what you want to do? You want to loop through. Okay, so remember you used to pass optimizer in model compile, isn't it? Model compile loss MSC. Okay, optimizer is equal to this guy. For every time it loops through, it gets a different optimizer, and it after getting the optimizer, remember this will take a lot of time to execute. Okay, this guy is still executing. Okay, so this is like a fit function which gets invoked. Nothing surprising. It's almost the same stuff, right?
It's a model.
Model, yeah. So now that okay. So if you have to find best epoch, best model. It will take a lot of time. Yeah. So what we did here. So this is cool so far, right? We load the model with weights and the highest validation. We have configured early stopping because if you do not do so, it will take a lot of time to actually run through the stuff. That is why early stopping. It already stopped. OS error. What is it saying? Checkpoints error. Achha.
So probably you have to create a directly checkpoints.
To create a directly checkpoints. Yeah. So I should do. I'll store it in my graph.
First we are comparing training, then again we are running the best model weights.
So here you are till this point you are creating the model, okay, with a particular optimizer. Then for that stuff you are finding what is the best accuracy for that stuff as well. For each optimizer itself, you have your curve goes like this, right? Okay, I mean it fluctuates and all that. You want to find what is the best model among it, right? What is the best model? Then you're creating a model using using what is the best model, right? So using the best model, you're finding you're saving, of course. I mean you're loading the weights which was already stored. Then you are again computing with test data. Understood, right? So these things you're doing with train data, and once the training is done, for each optimizer you are finding which was the best what are the best parameters for that. On finding what is the best parameter, okay, you won't find it the test accuracy.
So here it will for each and like all the 6 optimizer it will find.
See, it only stops some errors as well.
Can we To see which optimizer it has.
Oh, huh? Yeah, the reason why here also there was checkpoints folder, right?
Can you have a look at which optimizer it has to do?
We can see that it will show actually. The table it will generate, right? Here it will add the optimizer name also. Append best see, it is adding the optimizer. So at the end of it, right, it will show data frame which is of best optimizer, test accuracy, train accuracy. It will show in the calculated format.
So here we get accuracy for each and all the 6 optimizers. So then we have to take that optimizer and plot the graph.
Right. Plot the graph or just a table. Right. This results is that. So you'll see it will stop actually. Each of them it will not take a lot of, hopefully it doesn't take a lot of time. Stop.
There is other code running now. Your CPU is 100%.
Easily.
So TensorFlow will take a lot of CPU computation.
It's not meant for CPUs, I would say. That's the problem.
But when we doesn't have GPU, it is taking full CPU.
Yeah.
Even a small code, it's taking 100%.
That's what they say. TensorFlow takes a lot of there are no GPU CPU. That's what Amazon is for on the MXNet. The computation time is faster. So
it's actually heavyweight.
Which one?
TensorFlow
is heavyweight.
Good for server high. See, it stopped. At this at 451th epoch, it realized that it's fine. It doesn't need more. Yeah. So this is very good parameter. Early stopping.
But epoch you have given 200, right?
So here we configured it callback, right? In callback we configured early stopping. That means if for 200, your patience for 200 value, if it doesn't change, it will stop. It will change in 451.
So now it will print the values?
Yeah. No. It will happen for all the optimizer, right? It's taking around 70% of my CPU.
And that's the thing in TensorFlow, that's what they say. I think that's Google is working on, I think. Because otherwise, MSNet is.
Then they'll give their own programming language.
Not programming language, they may come with a new TensorFlow with this fixes to have the more computation. Yeah, that's what similar keras we have, right? In the MSNet, they used to have the blue card that runs on top of this one.
TensorFlow?
No, not TensorFlow, MSNet. MSNet is a framework. All this TensorFlow, MSNet, C and DK are all framework.
So this faster compared to this one.
MSNet is because it's faster and the computation time is fast. That's what the TensorFlow has. And that mainly they use it for the language natural language processing. They go for because it should not take a lot of time. Really fast.
Multiple values
for all the optimizers. 5 optimizers, 5 or 6 types are there, right?
Maybe 6 values.
Then it will show. I think it's releasing a couple of more, then we can know which optimizer is best.
We should get 6.
GD, AddMax,
Yeah, this is 3 optimizer. So in first optimizer in 451, next optimizer in 382. Yeah. Got it, right? So this is how you would actually configure test. So callback is definitely. Let's go to the previous guy.
Regularization, it will take half an hour. CPU is full. Only should have put one cloud. Completed? No.
No.
Still 250 only one.
Okay, in parallel, let me just show that adding dropout, huh?
Yeah.
So that will be finished with
Tomorrow we'll start.
yeah, CNN. Yeah. Do a little bit of reading on CNN if possible. I mean, though I'll start from the basics, but still, it's two things are
Probably collaborate.
no, I need this data. I can do there.
Yeah, collab we can do this. You give the data set and that means so
Collab, the thing is, if it is here, I can easily, I mean, I can do that, also download, upload and all that, yeah. Then I'll not be using it for re-editing. I mean, of course, for me, it becomes a two-step process. Let me see. Okay. Yeah.
dropout.
So regularization is one technique, of course. Dropout is another.
So dropout is a kind of regularization.
Yes. I mean, kind of a little superior, but more CPU intensive.
For the large data set, if you apply dropout, regularization, optimizers, so it will be a model, we will get a very good
very good rate. But doing this experiment, that is why now you understood, right, why deep learning didn't grew till early 2000, because each of them are so CPU intensive. If you're a researcher, you will never end up your research, right? So people had to dedicate more than 10-15 years. When people who are now the pioneers of deep learning are the one who had to dedicate a lot of years, and eventually this thing is reality because of the computation power these days. Okay.
Including everything in the code, I think takes computation is
very
extensive.
You can see this thing will also run. So yesterday that guy got finished, I think afternoon.
Oh, afternoon.
This is normal machine. No, you have a GPU desktop. When I do there, it is pretty okay. Okay. Huh? Yeah, no graphics card. There is actually media guy who comes for video editing, and I just tried it once. So it's pretty good.
Okay. That Collaborators runs on GPU?
I think it's shared infrastructure. So of course it will be GPU and all, but how much of GPU we are making use of it?
So when you want to run in Amazon, you will you want to run it particularly.
Then as when you are paying, then you know what you're getting. Here it is free, so okay. So I don't know what is the GPU version and all that. But when you're paying like Amazon or Google, if you pay that I need this much, then you'll get it for sure.
Oh, then you can calculate how much GPU
Yeah, of course, of course. Yeah, the 8 GPUs and all the 244 GB machines there. So they will do it. I mean, if you pay, then the world is yours. Data.
Small data.
So I'll copy paste the. Remember, we removed some features, added some features. I'll copy paste those strings. Okay, so from the entire data, what you're doing, we're just dropping these features, and few of the columns we are converting into one-hot vector. That means the column will be converted into vector, 1 zeros and all that. Okay.
Same way.
Right. We want to normalize some of the features. Okay, we're normalizing this feature CNT temp, humidity, wind speed.
That's the same thing which we did.
Same thing, I'm copy pasting it. Okay.
Why only we are talking those for any specific?
That we think, that it is not important in predicting bike journeys. This is a basic assumption that we are doing. I mean, not really a calculated assumption. Okay, so we are not relying on just to minimize something from the data.
But this also they have to guard into the data. And
This is autoencoders you might use and fine tune it. Okay.
This one we spend a lot of time on. Most of the time.
Yeah, in mostly competitions, that's why neural network. If you see a lot of top results are coming from deep neural, CNN or RNN now competitions, right? Those are the one which is winning prizes because there you don't have to bang your head to find which one is better, right?
Which it automatically.
That is the purpose of neural networks, right? It will find it for you. Okay, just that we want to minimize the time and we think that it is not
So
important.
this is like basic code of that. Behind the screen.
Oh, yes.
That's what's not easy.
No, I mean the thing is, the learning should be layered wise. I mean, first I'm not getting lot of things in details. Okay.
I don't know how you learned that.
Huh?
You are yesterday thinking how you learned.
No. It is the same way that I am teaching you, right? That's how I learn. You have to, I mean, the way we learn most of it, you have to omit details many times. If you stuck in details, you lose interest. So that's why I say, okay, don't worry that the details, callbacks and all. Just you know it for now. Later on, you'll use it multiple times, and you say, this is how there's more details to that. But if you learn it the library wise, right? This function is there. This is one library. This one. So 2-3 days after that, you'll okay, enough. So don't do that because we don't have that much of time. First of all, okay. So we need that layered approach. First, try it in a higher level. So that's why keras, TensorFlow, both should be discussed. If you do too much of low-level coding using TensorFlow, again interest will be gone. Like, the interest is main thing here actually. So now when you see, okay, these are some real data, you're working on some real data, get some real output here. It's not bad. Like you tried with regression, you tried with logic. It's not bad. It's working at least. You have a motivation to work on it tomorrow. That's how we run it. Okay. So okay, so this is precisely saving the final match. I mean, which are the column we are using for this is the target, this is the train test data. I mean, just some way to do that. I mean, doesn't this is in material code. Now is the important part where we will be configuring the dropout. Okay, I think we already remember the previous diagram, right? The without dropout diagram. So I'm not doing that. Right. I'm just configuring the dropout in this case. Okay, this is right. See, the only thing that you're doing here, adding this dropout layer. Right. This is the dropout layer. This is the dropout layer. So for each layer, we are adding the dropout.
This is the last layer.
Last layer. Okay. So actually, last layer there is no edges, right? That's the dropout. Last layer.
So here is the arrow mark,
right? And 0.20 means 5 times you will test for each of the edge. What is the essential goal? Essential goal is to find the weight, right? To find the weight, what you have to do here is you have to 5 times you want to find the weight before confirming this is it. So that is why you are giving a dropout of 0.20. Dropout means how many times you want to try out to find the weight of the edge. Like you remember, just compare it with random forest. In random forest, you try out many decision trees to find out what is the optimum, combine the results of those decision trees to create a forest, right? Similarly, you will try out five times since it is 0.20. Like every time, whatever weight you are calculating, it is attributing to 0.20 times of it.
So if it's a 0.4, then it's a 10 times or like
no, 0.4 it is one base of 1. So that's way each weight calculates 0.4 times, and last one it will not be.
So 0.2, 0.4. So it will be 1 means then only once only.
That is
So
by
it's
default.
0 to 1.
That is by default. Yeah, 0 to 1. That is by default. And every time when you're doing it, it is actually okay. So now you are. So you saw the process, right? The process is pretty much this: you get your data ready, create your network. Now, whatever new concepts you add that spice to the network. This is if you just don't do anything, it's a plain vanilla curry. After that, you have to keep on topping, spicing. Then it will give you more results, right? After that, you have to compile the model, right? Give loss function optimizer. You might change optimizer loss function also. Write that code. Then after that, you have trained the test data. Using test data, will find the validation, how good is it. So the process is pretty much same. And as long as you understand the process, you take in a problem, you should be able to solve it. In the initial days, right, you will be not be like 50-60% will be getting. But as you learn, okay, let me do this thing. Suddenly you will get 20-30% jump. Okay, then you are at that level, 80% level. Then you okay now I know this regularization. Let me do that. Next level, CNN takes you like I think MNIST in DNN we got an around accuracy of 92%, right? If you apply a plain CNN, you will get 99%, 99.2%. If you do more fine tuning, the best result of MNIST data is 99.79. Okay, that is the best result. That is a benchmark result. Nobody has done it beyond that. I mean, there is a web page which talks about. I mean, everybody's submission is increasing. I mean, the decreasing order of efficiency, it will show it. Okay, so I don't. There is some website. I know which is there in one of the tabs. It's not a name we can easily remember, but it will show that this is the benchmark. So gradually you will get there. Okay, let's see this. Oh, sorry. Okay, and This is a more and the fit function will fit function will return you the accuracies and history of this thing.
Callback. Here also
Yeah.
having the history callback, the same thing.
Here you have this actually. So this is your history. This is the model drop. You're training the model, and whatever results is there, it is getting stored in history drop. There it goes fitting. Batch size is not
Batch
good.
size. Batch size and epochs, I think we can define.
Yeah. Okay, after that, we'll be basically plotting the graph. Oh, all this is finished now. Let it happen. We'll plot the same graph. Okay, let's see. Understanding regular. Let's see this. See, this is done here, right? Okay, we want to see the graph now. Remember the graph earlier? It was
0.2 and 0.
Yeah, like this, right? We want to see, this regulation really work.
Completed.
Violation errors should decrease.
See this. Pretty close, right, to that. So the final model, let it be this. So you can see this is somewhat
But there's a lot
of noise, yeah. So maybe this is one thing. Okay.
To use dropout.
I mean, for some
along with this regularization.
Yeah, maybe that is working out better for us.
Because that hit all this noises within.
Here there is a lot of suddenly it is going out, then it is again the regulations coming in and handling it. So if it is because of that, right? Sometimes because of the algorithm, when it goes out, the regulation hits in the next cycle. It staples it. So we can choose a model here.
So if you apply L1 or something, the noises will go away, or it will be still the same. So different types of
right. Different in different cases. Sometimes this our noises may not be this steep.
Steep.
Okay. So sometimes maybe some algorithm may be throttling. So as you noticed, right, that okay, it is working, but there is some problem. People would have this is a common observation, right? I mean, the scientists would, oh, this is working, but it has a problem. So they would work in the next stage and can do with your. What is the next class? Right. So we want to see which one is best for us, right?
It's still running, right?
No, this is done.
Keeping the accuracy, right? It is not able to do it.
You can see here, yeah. This is like
So
Adam worked out pretty well, right? Test accuracy is around Adam, right? So this is the winner.
Adam. Most of the time, Adam is better.
Yeah, most of them. We use Adam in CNN.
Even if zero, HTTP has not.
I think there is some issue. So.
And this epoch is during the run for this one iteration, and we got.
There's some issue with SGT. Yeah. So here, I mean, we can leave this. But other guys, among other guys, in 99 iteration itself, it got the better result.
But in Adam, I think gave 62. Accuracy is more, but it took more epochs.
More iterations, yeah, quite more. Yeah.
So we have to also look into number of epochs, or generally accuracy is the parameter, right?
Yeah, accuracy is definitely a parameter, but you should see that what is the accuracy gain if you're writing 10 times. Right.
If
So
you achieve it 1,000 times
compared to 10 times, yeah, exactly. So in that case, people go for okay, this is a better model. It is converging faster. Right. Okay, but again, this is a subject of developers. I mean, this is your job basically ends with showing this to the customer. Right. If you are envisioning your job, okay, this is the end result. Okay, this is what I'm creating different models. Forget about what these are. This is the accuracy. This will take this much time. This will take this much. And right, because that is the purpose of optimizer, right? Yeah, maybe we can, if you fine tune with that optimizer more, we get better results. But the purpose of optimizer is to converge your okay, I'll upload all these files and the videos.